Hello, this is Trevor Hardy. I'm a power systems research engineer at Pacific Northwest National Laboratory, and I am one of the authors on this paper and a member of the Helix team, and I want to provide a short overview of this paper that we've written here. Um, in case you don't know, co-simulation, the focus of this paper and the Helix platform, is a technique that provides a method by which multiple simulation tools and models can be tied together and exchange data during runtime that allows them, doing so allows them to produce a larger and more complex system model than would be possible with just a single tool. So this co-simulation idea allows us to model systems that haven't previously really been possible to do because they span traditional simulation domain boundaries. And Helix is the United States Department of Energy co-simulation tool. Very specifically, the Office of Electricity, and Chris Irwin in the Office of Electricity has funded this work along with Ogohi Yon out of the Office of Electricity, Energy Efficiency and Renewable Energy. The two of them have funded this work over the past few years, and this paper is kind of an overview of all of that work that's been going on for those past several years. Uh, a little bit more specifically, this paper walks through kind of the software design of Helix so that you can understand the different pieces that are involved there. The basic concepts of a Helix co-simulation, how to make a simulation tool, how to modify a simulation tool or make a simulation tool so that it's able to participate in a Helix simulation. And then lastly, there's a huge set of examples that we're looking at that provide examples of how Helix has been used in real world research analyses. So we're going to go through that. Before we go any further, though, let's look at the software itself. If you just want to jump in and get your hands dirty, the the Helix library is up on GitHub. GMLC-TDC is the github.com is the project name. There's the Helix library itself, which is right here, and you can download that. The latest release is right here. You can click on that and download pre-built binaries. Obviously, if you want to build that yourself, you're more than welcome to. We also have a ton of examples. The ones that I usually point people towards are the ones that are associated with our user guide. These are um, all Python-based examples. So the idea is that these are the easiest to use and are the quickest to kind of pick up and go with. Uh, the user guide itself, docs.helix.org. This is a read the docs site. We provide a ton of information here, including installation guide for depending on which languages you want to use Helix with. There's different paths you can take to getting Helix installed. Also, like I mentioned, there's this user guide, user tutorial that walks you through um, a number of different concepts, kind of talks about the concepts, and a lot of these actually have examples associated with them. If you just want to jump into the examples and see how those work, you can click on over here, and we've got documentation on each of those examples. As I mentioned, there are a few language bindings that we've associated with Helix. The most popular one by far is the Python bindings, python.helix.org. We've got API documentation here. I spend a lot of time programming in Python and programming Helix in Python, and I come here very, very regularly because there's a number of APIs, and knowing those signatures, knowing how they work is important. Similarly, we've got a Julia binding, same deal here. How to install it, which is mirrored in the user guide up here, and then the API itself, how to work with that. So yeah, if you want to get started with Helix and want to just play around with the software, that is the way to go. So that said, let's jump into the paper itself. Scroll down. So let's starting out section 1, introduction, why we need co-simulation, what it does. Section 2 is kind of the start of the paper proper. Design of Helix. There's a lot of details in here. Even though this paper is relatively long, it's always just kind of a summary and an overview, a fraction of what we wish we could say. But this is a good place to start. Design priorities and philosophy of Helix. This is important to go over because it's a little bit different than some of the other co-simulation platforms out there. So I wanted to spend a little time on it. First, right here, we can see in this bolded list, we wanted to make sure that it was as easy as possible for simulations of all kinds to work together. Most of us, the authors on this paper, kind of have a power systems background, and that is a lot of the applications that you see for Helix right now. But it is a generic co-simulation platform, and we, as you'll see in kind of the examples, we've incorporated a fair number of different simulation domains into Helix. All of them kind of interact with the power system in one way or another. But Helix is generic, so you could incorporate any kind of tool for any kind of need. And we wanted this to be something that could be done so as to allow as many tools as possible to be co-simulated. Item number 2 here. This is where things start to get a little bit unique. Simulation tools can't impose restrictions or requirements on each other. We call it instance of a simulation tool a federate. And then following up with that, or very related, simulation tools should maintain individual control and autonomy. So between the two, you can kind of see this philosophy that Helix wants the simulation tools to be responsible for themselves and to coordinate kind of in a more voluntary manner. We don't want simulation tools that must have another simulation tool to work and that they send control signals back and forth to each other and have strict requirements on each other, things like that. We wanted to leave it up to those who are integrating the simulation tool to best figure out, how do I make this work as a good citizen in the Helix ecosystem. So we kind of have this more open, egalitarian approach to co-simulation. You can see here with points 2 and 3. Points 4, good software practice having a layered implementation. There's a diagram later down that you'll see briefly. But the APIs are built on top of APIs, and the software designers for Helix have spent some time trying to figure out which functionality needs to be in which layer, and having those layers of abstraction allow for easier maintenance and implementation. And then lastly, centralized control. Again, this is almost part of 2 and 3, but a little bit more specific to the Helix library itself and the Helix applications. We wanted to minimize the need for one entity in the system to know everything about something. And we did that because other co-simulation platforms we've seen and used in the past have really struggled as you start to scale up. So it's a lot of them perform just fine when you have a relatively limited number of simulation tools and models running, 2, 3, 4, 5. Almost all of them perform just great. When you need to do something kind of ambitious, shall we say, if you wanted to model the power grid of the Western United States and have potentially hundreds of thousands or even a million or several million federates, that's ambitious. And if you have one centralized entity that's responsible for maintaining a lot of control, things just fall apart. You don't get performance that you need out of that. There is a paper referenced in here in the study that has done scalability testing comparing Helix with other co-simulation platforms, and Helix has come out looking really good on that. So we're really happy we were able to achieve that for our Helix itself. So moving on here, there's the diagram I was talking about with the Helix API layers. If you want to dig into that, feel free. This next section, the federate types. So as I mentioned, a federate is an instance of a simulator. So if you have some kind of controller that you wrote in Python, that may have one source, controller.py, but you may have 20 things that are using that same controller. And each of those times you instantiate controller.py, we would call that a unique federate. It has unique states that it's tracking. It has unique signals, perhaps, that it's getting either as inputs or outputs. So there is a difference between a simulation tool and a federate. Federates are instances of simulation tools. And in Helix, we have two different types, or actually three. The combination federate is a combination of these two, but two different ways of thinking about federates. One is a value federate. A value federate is an entity that sends and receives physical signals. So these are things that have units like a voltage or a current or a power or even like a weight, things like that. A value always exists. Its quantity changes over time, perhaps. So value federates focus or primarily or only really, a value federate only sends and receives these kinds of signals. A message federate may have information that is similar to a value federate, but it has been chosen to be represented in an abstract way. So you can think of a sensor The output of a sensor typically is some kind of abstracted information. It's measuring the quantity, but it produces this output signal of some kind. Messages are kind of a little bit more like uh, packetized information that is sent and received. So this is more analogous to like communication systems kind of get involved here. Like I said before, sensors and controllers. Controllers will receive the control signal and then execute it. Sensors generate those. So it can be confusing. If you need to kind of dig into the details, you can look at these sections of the paper. And then a combination federate is just like it says, kind of a combination of the two to help clarify that difference. And it's important to kind of think about it as you're getting a co-simulation together. We've got this table right here, table 1, talks through the differences that are there. Section 3, and obviously we're skipping over things, lots of details you can get into. Section 3 here is about how do you actually implement a helix-based co-simulation, a helix federation. So that the the work of an integrator is to take an existing simulation tool and add the Helix API calls in some way to that tool. Generally, there are two ways we think about that. One, if the tool is open source, you're able to obviously download the source. You can, import the appropriate libraries or include them in some way, and then find in the source code where do these special Helix API calls need to be made so that when this tool is participating in a co-simulation, it is sequencing its operations in the right way so that the results that it produces are meaningful. If the tool isn't open source and it has a API with the appropriate functionality exposed, you can write effectively a wrapper, like a Python script that imports that tool's API library and then imports the Helix library and then writes functionality into there that allows that tool to appear as a Helix federate. So that tool makes calls to the, or I should say that wrapper makes calls to these API to the tool itself and tells it to do some functionality and then takes the results of that functionality and sends it out to the rest of the federation with Helix and then gets new information in and applies that to the simulation tool. So you kind of got this two-stage implementation. If you have a simulation tool that doesn't do either of those things, it probably is not going to be able to be integrated as a Helix tool. So those are kind of the requirements. We've got some examples here in the paper of how that goes. This Helix Federation lifecycle, this diagram right here, I think is a very useful diagram. We won't be able to go over it in detail, but it kind of outlines the basic steps that every Helix federate goes through. Lots of variation, lots of details across all the different simulation tools. But the idea being that there's a process by which there's APIs to create a federate, you initialize that federate, and then you start the simulation proper. And that consists of this main loop where you request a simulation time, Helix will grant you that time, you get inputs from the rest of the federation, update your internal model, so you apply those inputs, calculate something based on those inputs, and then send new data out for the rest of the federation to use. And then this loop repeats over and over until you're through your simulation time. Again, further details in the paper. It's a good place to start if you have some familiarity with co-simulation. And then the big section in some regards. The long section here is scrolling, other important things you can read, scrolling. The applications of the Helix co-simulation. So this is, there's tons of papers. You'll see at the end, I'll show you just the two pages of references we have. I'm just gonna highlight a few here. I'm not gonna look at that one. We're starting here, figure 7 is a simulation, a co-simulation that we did that was actually simulating the bulk power system, or I should say, it was retail and wholesale market operations we modeled with different simulation tools, and then looked at the kind of the many different aspects of how that power system operated. And one of the ways we looked at it is this, what we called the river of money, the flow of money, for how residential, commercial, industrial customers, the revenues generated by them, how they flowed all the way through the system. So for example, the energy charges would be part of the bills associated with these customers, and those were fed up to a local utility, a distribution system operator, and they used that money, some of it to purchase energy, some of it to pay for their operation costs, et cetera, et cetera. So you can kind of see how it gets broken down through here. And this, you need co-simulation to do this because the tools that are required to model at good enough fidelity require working across simulation tool domain. Uh, yeah, I was involved in this paper, this project, really great project, in my opinion. Take a read. Figure 9 here shows an example. So this is inverter-based resources uh, doing a transient analysis. So these inverter-based resources were modeled in a distribution system simulator, GridLabD in this case, and then that was tied into a bulk power system model, PSSE in this case, and then a transient analysis was done. So as some bulk power system event happened, a generator tripping or a line going off, classic kind of transient analysis things, the inverter models in GridLabD were set up to handle these very small timescale responses and to simulate how inverters might respond to that. Um, and obviously, I shouldn't say obviously, the inverters were modeled at different, conforming to different standards. So grid following, grid forming, that kind of idea. So you can see based on the level of penetration and the settings on the inverter, the response to that bulk power system event in the local power system, you can model that and simulate that. So again, prior to something like Helix, it would have been very hard to model model across the transmission and distribution simulation domain boundaries. So it's great. Helix allows this analysis to happen, and we can see the effects now of this as inverters have reached higher penetrations in the distribution system. This diagram here, figure 10, is really nice because it shows that we're not just doing transmission and distribution, though that's a common use case. In this case, we were actually doing just distribution system and very specifically microgrid. So we had these microgrid agents and device agents that were written in Python. The device agents talked to GridLabD and provided control signals to assets in GridLabD. But the communication between the microgrid agent and the device agent was intermediated by a simulation of the communication system in NS3. So the cyber layer. And that allowed you to do all kinds of modeling that you wouldn't be able to do otherwise. Um, you can model congestion in the communication system and how that might impact the agent operation or the controller microgrid agent operation here, device at microgrid agent. You can model adversarial events in the communication layer. What if there's somebody who is executing a cyber attack in this microgrid? How might that take place? You could model, what if this was implemented with a particular technology versus, another technology? Which one has better performance? Those kinds of questions you can start modeling when you include an explicit communication system layer in the co-simulation. Move on here, figures 11 and 12, you can see here, these are both platforms in and of themselves that have been built on top of Helix. So again, platforms built on top of platforms. This one over here in figure 11 is GridAppsD. GridAppsD does a few different things, but one of the things it tries to provide is a simulation test bed for those who are developing distribution system applications. And the idea is that you can take your application and in GridAppsD kind of plug it into their software infrastructure and evaluate it against distribution system operations, potentially communication system operations like we were just talking about before. And it provides a way that you can kind of abstract away the application and what it does from the test bed itself, that those don't need to be integrated tightly in one piece of software. GridAppsD has found a way to kind of break that apart and abstract it. Figure 12 over here, this is another simulation platform that I've worked on. This is for the Transactive Energy Simulation Platform, or TESP. And similarly, it provides a test bed for evaluating transactive energy systems, as the name implies. So it has built-in models for not only the distribution system, but the bulk power system, commercial buildings, communication systems, and then market models, market agents, those kinds of things, and ties all of those together. Those are all each individual pieces of software, ties them together with Helix, and allows then these transactive systems, which almost always cross domain boundaries, to be evaluated and developed. Lastly, I think, yeah, we're gonna again skip through a number of these other studies. Figure 15 here is showing a different kind of integration or a different kind of tool with Beam, which is a transportation system simulator. So as electric vehicles become more popular, the impacts of transportation on the power system are going to become more significant. And this study here that's referenced in the diagram, uh, shows that through the use of Helix, we were able to build models of the power system and then build models of the transportation system and then see how does the impact of charging management or lack thereof, what are those kind of impacts on the bulk power system, and do it in a way that accounts for the particulars of how the transportation system operates and how vehicles move through that transportation system. Yeah, lastly, like I said, there's a ton of references that we've included here. These aren't even all the studies that have been done with Helix. So I would recommend if there's something that you're thinking about doing, take a look at these references here. There's probably something similar to what you've already done. If you're a little bit lucky, that code will be out there for you to use, and you can, start from somewhere closer to where you want to be than starting from scratch. Um, Again, this has been a relatively brief overview of the paper. I'm hoping this has been helpful. If you want more details, you're going to be able to read the paper. So thank you.